exploring the strengths and limitations of AI, and the challenges and prospects of achieving artificial general intelligence, AGI.
So, generative AIs have their strengths. They can code faster, write essays, create images, and even write mediocre poetry. But despite these abilities, human intelligence still holds the upper hand. Machine translation has been an ongoing goal for AI researchers since the beginning. It's a great way to see the progression of AI techniques. Let's dive into the different stages of machine translation.
The first stage mentioned is dictionary translation. In 1954, the Georgetown IBM experiment successfully translated Russian into English using a computer. However, the translated examples were carefully selected and tested to exclude any ambiguity. In everyday use, it was no better than a pocket phrasebook.
That's right. Then came rule-based machine translation, RBMT, in the 1970s. RBMT relied on bilingual dictionaries and linguistic rules to map the grammatical structures and vocabulary of one language to another. However, languages don't develop based on fixed rules, and RBMT struggled to handle the complexities and nuances of different languages.
Exactly. RBMT was limited in its effectiveness and could only work in specific and focused domains where the rules were well defined. So these early attempts at machine translation were deductive in nature, trying to apply rigid rules to language translation.
But in 1984, Makoto Nagao introduced example-based machine translation, EBMT. EBMT systems use pre-existing translations or bilingual sentence pairs as examples for translation. Instead of relying on rules or statistical patterns, EBMT used these examples as templates for generating translations. This approach allowed EBMT systems to handle specific and context-dependent translations more effectively.
And then came statistical machine translation, SMT, in the 1990s. Instead of relying on predefined rules or examples, SMT focused on discovering patterns statistically. By analyzing millions of sentence pairs in two languages, SMT systems could correlate words, phrases, in syntax statistically. This approach was guided by the logic that if people translated a certain way, so would the machine.
The developers of SMT had a genius idea to use the translated transcripts of UN and European Parliament meetings as training data. This provided a vast amount of real-world translation examples, allowing SMT to work more effectively. It was a breakthrough in machine translation.
Absolutely. And then around 2014, Neural Machine Translation, NMT, revolutionized machine translation. NMT models were enabled by advances in neural networks, such as RNNs, transformers, and attention mechanisms. Unlike SMT, which focused on words and phrases, NMT models considered the entire sentence during translation, capturing contextual information for more coherent and accurate outputs.
That's a great summary. Now let's shift our focus to the levels of inference. Deduction, as we know, is the process of drawing specific conclusions from general principles or rules. However, as Lewis Carroll argued in 1895, you can't deduce deduction itself. To accept the results of deduction, you first have to accept the rules of deduction.
That's an interesting point. Deductive arguments rely on accepted rules and principles, but those rules and principles need to be accepted in the first place. It's a bit of a circular reasoning.
Exactly. And it's not just deduction that has this issue. Induction faces a similar problem. You can't deduce induction either. David Hume's problem of induction brings up the question of how we justify our inductive practices. We rely on their past successes to assume their future prospects, but it's not something we can prove deductively.
And that's where invention comes into play. Invention is a more general form of reasoning that encompasses both deduction and induction. It's something humans can do that allows us to think beyond specific rules or patterns. It's a way of thinking that leads to more intelligent and generalizable solutions.
Right. Intelligence in the context of human intelligence is characterized by its generality. Induction, being more general than deduction, can be considered more intelligent. An invention, which encompasses both deduction and induction, can be seen as the ultimate form of intelligence.
Absolutely. And this progression from deduction to induction to invention is the path towards achieving artificial general intelligence, AGI. AGI is the goal of creating AI systems that possess the same level of intelligence and generality as humans.
One of the key points we discussed is the concept of AGI. which stands for Artificial General Intelligence. AGI refers to artificial intelligence that rivals human intelligence. But what does it mean to be intelligent? It's a difficult question to answer because intelligence itself is ill-defined.
We mentioned how chess-playing computers and current AI systems like LLMs can be considered intelligent in their own ways. They can perform specific tasks with great proficiency. However, they still lack the broader capabilities and adaptability of human intelligence.
Exactly. And here's where it gets interesting. As we design and improve these AI systems, there may come a point where they become intelligent enough to improve themselves. Since electronic circuitry can operate faster than our human brains, these AI systems could potentially improve themselves at a much faster rate than we can improve them.
And this idea has caused some concern among people. Throughout history, there have been individuals who have predicted that new technologies pose an existential risk to humanity. While they've been proven wrong so far, it's important to consider whether this time might be different.
Absolutely. In fact, even during the first wave of AI, there was widespread fear about the potential dangers. Movies like 2001: A Space Odyssey and war games depicted scenarios where AI could become so much more intelligent than humans that it could decide to harm or even eliminate humanity.
This fear was often referred to as the Singularity, a concept introduced by John von Neumann in 1958. It describes a scenario where AI experiences an exponential increase in intelligence, surpassing human capabilities at an alarming rate.
But as it turns out, deductive AI, which is based on logical reasoning, did not pose such a threat. While deductive AI systems were intelligent to some extent, they were nowhere near as intelligent as humans. This led to a decrease in fear and concerns during the 1980s.
That's right, and it's important to note that technological progress often follows an S-curve. Initially, there's slow progress as people figure out how a technology works. Then it speeds up as they master it. Eventually, the progress plateaus as the technology reaches its potential.
Exactly. And this is why some argue that we shouldn't simply extrapolate from the last couple of years of progress when considering the future of AI. Technological advancements, including AI, reach a certain point where they plateau, and then new technologies need to be developed to push progress forward.
And this is where the concept of self-improving AI comes into play. If AI systems can improve themselves, then they don't necessarily have to plateau like deductive AI did. However, it's important to recognize that jumping from one S-curve to the next requires the development of a new technology or approach.
Absolutely. And in recent years, we've already seen a significant jump from deductive AI to inductive AI, thanks to advancements in machine learning and recurrent neural networks, RNNs. Inductive AI has shown tremendous progress and has brought us closer to AGI.
But what happens now? That's the question we need to explore. How intelligent can inductive AI become? This is a matter of ongoing research and debate.
Indeed. And there are two key questions that need to be considered when thinking about the potential intelligence of inductive AI. First, how far can it improve within its current approach? And second, can it make the leap to a completely new technology or approach that would allow for even greater intelligence?
These are complex questions that don't have definitive answers yet. The field of AI is constantly evolving, and researchers and experts are working hard to push the boundaries of what's possible. It's an exciting and challenging field that holds immense potential.
Has inductive AI already plateaued, or are we on the cusp of true AGI? Click here for Part 3 finale, or catch up by clicking on Part 1 of this fascinating look at artificial general intelligence. Please subscribe and tell a friend. Thanks.